So you want the computer to be on both sides?
You want the computer on both sides?
So I don't think
Yeah.
okay. Just a whole thing. I'm saying that one part is not worth the one part that's all involved is not worth the one original. Which is stupid too. Yeah, it's a piece of cardboard.
The thing it's not even card stock.
Oh wait. Alright, cardstock. I'm gonna make my card so much like that much.
Oh, okay. So yeah, then you
Yeah, because I know my roommate was probably like $6,000 $1,100 deck, and I'm like, how do you have $1,100 on cards? Like, why can you spend that much money? It's just like it's terrible.
Oh, 94 is so bad around the road. Super bad. 4 to 7.
Yeah.
Well,
If you
yeah,
get there
I
before
worked
3, it's good though.
I'm leaving at 2:30.
Oh, yeah.
That's it.
Rip.
Go real quick.
So I worked in St. Paul over the summer, and then I worked with Mitch's mom, who was with me, so we drove all the way back from the last so we drove all the way through the strip, and it was
wow.
like 4 hours to get home sometimes.
You clear our
So I used to be a gathering. That's probably super cool with my deck that I bought all the time. It was like $15. Yeah, I thought it was great. It was the best one of my friends around time.
Every
This
time
was
I worked for his mom,
$1,100
he works the
deck.
night
What?
shift, so he would bring home like $1 in the morning.
No, but see, then I learned from him. The new, like, he has to play parts because I didn't.
No.
Because it was like, you play with like only the new sets. That's cool. And then you play with.
Welcome to the meeting number 7 in Physical Chemistry 1. Thank you for timely submission of the materials.
Thank you.
So you are encouraged to ask questions to your peers, and it will not go unnoticed. So the goal of the course is to describe chemical systems and characterize them, and due to this reason, we found that properties of electrons can be described only in terms of quantum theory. That is counterintuitive, and the best thing to get through this barrier is if you teach each other rather than listen. So the information that you're going to offer to each other will not be repeated in lecture, so listen, make notes if needed, or ask questions if something is not clear. And there is additional pressure that time limit. Some of you may have classes or lunch plans, so I will try to follow the time. So we are on the meeting number 7, and totally there was a chance to fit in about 44 meetings for the whole semester. So there are 6 postulates, and they cover different aspects of quantum nature of electron, and give my chance to learn your names, so you know who are which team presents the specific material. Also, if I applaud your effort to appear in class, and I hope you keep coming, but if by some reason you need to travel, this thing is broadcasted online, so if you are in Australia on Monday, you can still join and ask questions. What else? If you have never seen PC with Microsoft Windows, which I have, then I just give you heads up that it is what Microsoft thinks with full presentations in PowerPoint, and here are the first, second, third, fourth, fifth, sixth, right? So want to launch it, you just double click. And some of you like the Macs or tablets, if you do like see. So here's the symbol to put it on the presentation. So with this, I would like to announce first postulate of quantum theory presented by Alex Hart and Morgan Aguilar. Floor is yours. I will give you another comment and prepare. It is like 1 minute to go to stage, about 4, 5, 6 minutes to present, 1, 2, 3 minutes to answer, and 1 minute to walk back. So count this time as well. So floor is yours. Please. Go ahead.
Yeah, we have postulate 1. It's kind of important because the rest of the postulates build on that. So, I mean, there's not super advanced stuff. Well, there is, but there's not a ton of advanced theories going on here. It's just basically stating what all your other postulates will be built on.
It's kind of like the foundation.
Yeah, just hit go. This is the first slide. Okay. Because we did this and then I finished my part and then he edited it later at night. So what it says is every particle has position variables, n position variables, which are q1, q2, ... all the way up to qn. And they're specified by a wave function. So anything about that particle can be found by knowing its original position and knowing its wave function.
And yeah, they kind of just use that wave function in terms of kind of like electrons when they can't exactly predict its current location. They use this wave function as kind of like a way to kind of guess where it's at. They kind of know sort of the range in which it's in, and that's how they use the wave function in order to kind of predict where that electron or particle may be at certain times.
So the n usually equals 3 as labeled on the PowerPoint, but those n's would just be relative to positions, so like in Cartesian coordinates x, y, and z, how high, long, or just where you are is good, the usual good. And what I'm trying to say, different position variables. Another thing that's important is time. So time could be a fourth one, which is in time dependent, like Schrodinger equations. That's a big factor, and that's a big factor in just in general. And then other coordinate systems. I mean, like there's polar coordinates where you use circles and radiuses, or cylindrical coordinates if you're trying to do that for some odd reason. But yeah, do you have anything else to say about this one? So we kind of already went over some of this slide when we were talking about the original one, but
Yeah, so kind of like how I was saying earlier, kind of the analogy that I found online was sort of like if you were to put like an electron in a box, and then like it can have like this certain wave in which it can't be outside of the box or like in the box walls, but it can only be like inside of the box. And so then you can use these wave functions in order to predict kind of like each different part, like using each different part of the Schrodinger equation with like the, since it's built out of potential energy and kinetic energy, you can use those different things to kind of guess where it's at without actually like measuring it. And so that's kind of what this slide is kind of going over. Yeah.
Other than the other points that are on the slide, we basically made the last slide, so we just talked about that. Okay, there we go. So what this actually means is we can predict the motions of systems with the wave function and its initial position, because everything about this system can be just described in the wave function and its initial. So if you know the wave function and you know its initial position, you can know everything in its entirety about the entire system. So we don't have like the wave for a wave function. We don't have an equation off of just this one postulate. It's more theory. And like I already said, fourth variable to introduce is time. But yeah, so we need more postulates and more research data to expand on what the wave function would be and how to accurately figure out where an electron is.
Yeah, because you just kind of use this kind of initial step, and then as you build and add more things, more postulates, then you kind of are able to become more accurate with like your estimation, calculation, where that particle may be.
Let's see in the more slides. So, any questions?
Okay, let's thank the speakers. And we seize an opportunity to ask the questions. Later there could be quiz to check if you percept of this information. So ask them if something is not clear. I have. Can you scroll back, Widow?
First slide.
No. Yes. So 3 times the states per number of particles. Can you defend this statement?
Yeah.
If you're sure, or
I
tell
think,
something
I think
different.
I can, and you might correct me, but so every number of particle has a different state it could be in. So if you have 2 particles, well, each of them could be at a different space and time. So if you have x, y, and z coordinates for every particle, you're going to need a different location for that to be at. Correct? That's what I got from reading it.
Well, maybe you are right, but I have different.
Okay. I think you're probably right.
So if you have independent particle and each of them has like n states, and then you have second particle with another n states. Total number of states will be not 2n but n squared. So number of states to the power of number of particles. You may just disagree and argue, but we will go through it in the class.
So they're kind of like 3 to the n.
3 to the n.
Okay.
Okay.
Wait. N to the 3.
Yeah.
N to the 3, if there are 3.
But if there are 2 particles, there's 9.
N to the 2. Number of states to the number of particles.
Yeah.
So it's 3 to the n or n to the 3?
N to the 3.
N to the 3. So with 2, there's 8.
Mm-hmm.
With 1, there's 1 state. Because if you had n to the 3, okay, I'm confusing myself now.
More questions. Practical. How many variables would be for helium atom? If one electron has 3 coordinates,
3.
and the helium has 2 electrons,
Oh, then 9? Or
6 will be fine. We assume that the nuclei is just mute, But you're correct. 9 if you allow the nuclei to move. Okay, let's thank the speakers. We are just 3 minutes late. You see how it goes. So next presenters are Michael Odegaard and Edwin Reed.
Yeah.
So we're going to learn something about observables and operators. And floor is yours.
Sorry if you guys failed this quiz. My information isn't the best.
Okay, so we had.
Just a second before. Anyone who needs to leave sharply at 11:50. Okay, which number you present? Okay, fine.
Okay. We had. I'm Kaylin. This is Michael. We had postulate 2.
Okay, so what is postulate? Every observable corresponds to a Hermitian operator given by the following rules. So every Cartesian position has an operator, so like x is x, and that, and it's the same for y and z. So like for linear momentum, it goes from x to px. It's the same for, which is derivative of algebra, right? Which is the same for Y and Z. And to obtain the operator corresponding to any other observable, first write down the classical expression for observable in those terms, and then replace with the corresponding operator on the. So to summarize that, for every classic observable, there corresponds a linear quantum mechanical operator.
Okay, so what actually is a classical observable? A classical observable is any property you can measure with classical mechanics. So like energy, position, momentum, like basically that table that he gave us at the beginning of the year, it's like all of those properties are classical observables. And basically what postulate 2 says is that the operators represent the observable properties. Okay, yeah, so these are like 3 of like the main examples that we have on that table. So the observable total energy has the operator h hat, and then, which we've seen from the Schrödinger equation, which equals negative h bar squared over 2 times the mass of del squared plus v of xyz, which is r. R is the xyz. So in 3 dimensions, del is the second partial derivative with respect to x, the second partial derivative with respect to y, and the second partial derivative with respect to z, all summed up together. That's what this symbol is. That's del. For position, in 1 dimension, it's just multiplying x, which is represented by x hat, and then in 3 dimensions isn't on here, but it's r hat, which is equal to each of the individual operators multiplied by a vector. So like I times x plus j times y plus k times z. For momentum in the x direction is minus h bar times the first derivative with respect to x, which is the same for the y and z directions. So we mentioned the linear operators earlier. So there's multiple kinds of operators, but the main one we use is a linear operator. So a linear operator obeys the following restriction. If that linear operator is acting on a function, which is defined as the sum of I equals 1 to n of some coefficient, which is like some real number or imaginary number, times the function of whatever variables your operator is acting on. If it's linear, it's equal to the same sum of the coefficient factored out times the operator acting on that function. So some examples of like linearity, as you can see right here. So x to the n, if you take the derivative or integration, are all linear functions. Examples of nonlinear functions are taking a square root or squaring a function, which is different than taking x to the n.
Okay. So Hermitian operator is to do with the properties we measure, all 3 real numbers, like energy, position, and momentum, all 3 real, so operators have commutation. A physical variable must have expectation values and eigenvalue. This implies that the operators are variable. By computing the complex conjugate of the expectation value of the physical variable, we can easily show that the physical operators are their own Hermitian conjugate. Operators that are their own Hermitian conjugate are called Hermitian conjugates.
And then these are the equations on how to figure out if it's a Hermitian operator or not. And this is just saying like Hermitian operator is if it's.
That's it?
Yeah.
Okay, but then speakers, Kate and Michael. So questions. If they did confuse you with something, it's time to protest.
Will we be going over some examples of this in class later of how to convert, operate like classical observables to operators and other things when we like start to do homework with actual equations?
Yes, we do, but now it's time to ask questions to speakers, not to me.
Yes, we will be.
More questions? I do have two.
Oh, great.
So if you scroll to the first slide,
This one.
The fourth one.
what is a classical observable? Yes. So you gave. It's a tricky question. If there are no answers, do not worry. Just memorize it to answer later in the course. You gave very simple examples like position, momentum, and energy. But when you do experiment of characterization in chemistry, when you have like NMR instrument or spectrophotometer, do you measure position and momentum there? What are real observables that people measure? If anyone has answers, please give it. If no, memorize it and let's answer it during the course. I promise we will. Like intensity of emission when something is observable, and it is what we can predict by the end of the course with these tools. Okay, thank you for thinking about it. And the second question, scroll to the seventh.
The equation slide?
Next with words, yes. So it is not a question; it is comment. Main thing out of it that Hermitian operators are the operators that provide real eigenvalues. Real because anything we measure is real. Like the wave functions can be imaginary, but anything we measure in true instruments is real. Therefore, this setup for Hermitian operator is made. Okay, so these things are not made to torture young minds. It's all made by humans for humans to describe real nature. More questions to speakers? If no, let's thank them once again. So postulate number 3 about measurements will be presented by Bill Howlett and Gage Winjo. We do this thing. We're just 4 minutes late.
That's right. We'll go quick.
Go ahead.
All right, so we got postulate 3 in today.
Okay, so postulate 3 states that the only possible result of measurement of the observable in question is one of the eigenvalues of the corresponding operator. Measurement, you know, when we measure, we're looking for something, we're measuring it, and as we have here, the Copenhagen interpretation is saying that you know, it's a superposition until we actually do observe it, so it kind of exists in every possible state. Once we do measure it, then it the function itself kind of collapses, and we have the state that whatever state we measured, that's where it is now. Well, I guess we kind of went over in that last presentation, but again, we have listed momentum or position.
Yeah, now we know that observables can also be like intensity emission through NMR and stuff. So in quantum physics, basically we can change this into talking about operators for observables as well. Okay.
Okay, so I don't know which one to start with because they all kind of contain each other. I think I start with the eigenfunction, which is kind of the function which this, this operator. Yeah, kind of. Like, whenever the eigenfunction is acted on by the operator, it then is multiplied by the scalar eigenvalue and only by a scalar eigenvalue. And when this does happen, it collapses into the eigenstate, which is dependent on the measurement that we took.
What? I couldn't say it better. So please continue.
Yeah.
I think so, yeah.
Okay. Cool. So what are we satisfying here? Well, we're satisfying this first top part equation. Satisfying this equation here, this kind of eigenfunction where we have an eigenoperator, we have an operator, and then we have our eigenfunction. So basically what we're saying here is that measurements must always yield eigenvalues. And in that sense, the state is not necessarily completely the eigenstate initially. but like we said earlier, it can be in a superposition state, and then once we actually measure it, we can determine an actual state of the electron, which furthermore satisfies a summation of our eigenvalues multiplied by our eigenfunctions. So kind of going back on Hermitian operators, which is what started the last postulate. Again, real eigenvalues contain orthogonal eigenfunctions, perpendicular, so functions that are kind of crossing paths. Thus, an operator is Hermitian when it can always be transitioned to the other side and enter product. So if you see here, we have two eigenvalues. We can flip these two eigenvalues and eventually get this value called delta, which is basically the average of those eigenvalues. And these average value of all possible results basically shows us the probability of the electron in its state. So kind of summarizing everything that went on here, I kind of looked at it this way. So we have our wave function that shows us kind of the state of the system and kind of the probability distribution cloud of the electron, how the electron's moving. And from there, the wave function is subject to this thing called the uncertainty principle, which is that if we have like a measurement, we can simply, if we have a measurement such as position, it's useless to find momentum because that electron is constantly moving throughout space and time, and it's hard to figure out its future position. But if we were to find something like its momentum, we could predict its future. And it's all subject to other properties. But moving on from there, the wave function, like we said, collapses when we actually have a measurement which provides us an eigenstate that is observable. And so this eigenstate eventually leads to operators multiplying by eigenfunctions to get us more real definite values in a physical space. And that's basically it.
Okay, let's thank speakers. And it's an opportunity to ask them questions.
This slide's the second to last one before the sources. More on postulate 3. There we go. Yeah, that one. So is AJ and AK, are those two like positions or momentums of like an electron? Is that what it would represent?
They can be. They're two eigenvalues based off measurements. So they could be two positions, they could be two momentums, or they could be a combination of the intensities. They're just two measurements that we can identify.
Okay.
More questions? Can you scroll back?
Yes.
One more?
Forward.
Yeah, here.
Here? Okay.
Anyone found a typo here? For a point. Do you see any typo here yourself? So, index here as well.
Oh, sorry.
Okay, and can we, so it was, and let's go to the next. So there is something is hard for me to agree.
Okay.
About the delta function. Is everyone agrees with Bill's definition of delta function?
Don't know the functions.
Okay, then let me correct so that do not believe this statement.
Okay.
Then it's the average.
So this result of this integration, the nice property of wave functions that it will be, if they're good quantum functions, result of such integration will be either 1 or 0. So it will be 1 if index j is equal to index k, and 0 if index j is not equal to index k. So the symbol delta is used to just summarize this observation. So it's not average, it's just mathematical symbol. More questions? but really definitions of observables and collapse of wave functions were good. Okay, let's thanks. The next presentation of postulate number will be by Steven Lee and Joseph Lee. Oh, Joseph is not here. So here is the brave man. And we are still 4 minutes behind, so previous speakers didn't accumulate any delay.
Okay, so I had postulate 4. What is postulate 4? So the definition is a system in a state described by a normalized wave function, then the average value of the observable corresponding A hat is given by the expression. So this is what you basically, I believe you plug in your terms, and then you will get a value of A, which ends up being an eigenvalue. And the best way I could kind of describe this equation is, basically this is like you're normalizing everything. So kind of like vectors, how you normalize vectors. And so you do that, and then you end up getting just kind of your equation here. So using this normalized equation, then you'll get your average of eigenvalues. And from those, and so you can get multiple sets of eigenvalues. And from those sets, so how do you use these eigenvalues? So once these eigenvalues are generated, you can get them into a basis set, and then which can be used into a linear combination. And yeah, that's about all I had. It was kind of just seemed like it was just an equation and kind of hard to depict it.
Okay, let's thank our champion in being super short. You saved us. Now we are 2 minutes forward.
Yeah.
Any questions?
Where does
Everything is crystal clear.
the equation come from? Is it just from like the equation that you have to get the eigenvalue A? Where did that come from?
First question to you. It's not my.
Are you talking
The first one, the
first
big one.
Like where do you? What was the question?
Where would you find this equation? How is this equation derived?
I don't really know how it's derived. I just kind of did. I don't know.
Is it a trap question?
No, I'm honestly asking where was it
Okay,
derived?
let's try to answer together. We do know a property of eigenvalues, and we know property of orthogonality. So if the operator has its eigenfunction here, then it will operator will disappear. Instead, here one will get the eigenvalue observable, and here one would get the index of the eigenstate. So the number, the eigenvalue, can be put up front of the integration, and then the wave function star, this eigenfunction, need to convolute and give either 0 or 1.
Okay.
After you get 0 or 1, the functions will disappear. You get only the eigenvalue as a result. So by this construction, you'll get the eigenvalue. It's a way to kill wave functions, to remove wave function from the construction.
Okay.
Good?
Okay.
Satisfied?
Yeah.
Good. Questions to the speaker? E1, questions 2, questions 3. So let's thank the speaker once again. And the next presenter of the postulate number 5 is Joy Dahlgren.
Yep.
So it will be how if observation can change the system.
So the fifth postulate, I made this probably too wordy, but if you measure or observe the system in any way, the system is changed or disrupted, and it has to be manipulated to return it to its original state. It's basically the main thing of it. So if you have a result of a measurement corresponding to the eigenfunction and the state function, it's basically alpha r equals phi r. So in general, the measurement, if you change the measurement of the system or disturb it in any way, it has to be manipulated to go back to, it changes it when you measure it, so it has to be changed. So it has to be manipulated to go back to its original state. The fifth postulate pretty much outlines the statistical nature of the quantum mechanics, and it bridges the gap between the mathematical part outlined in the first four postulates and the experimental process of measuring it. It's usually one of the most controversial, supposedly. It's also known as the collapse of the wave packet. So the Hermitian operator can be known as the eigenfunction f of that is that small f of that. So identically prepared systems can be different, have experimental outcomes, even if the math is the same, but they can outcome, when you do the measurements, they can be different. Then there's the collapse of the wave packet, both normalized even in the measurement process replaces phi by that equation on the bottom there, instead of the square times the a sub n. So it kind of deals with time evolution as well. So when we talked about dealing with the time-dependent Schrodinger equation and time-independent, so that's kind of this basically what this talks about. So the H bar or whatever is the Hamilton operator, and it contains the kinetic and potential operators in one. And it reflects the nature of the particles or waves. It allows us to propagate the wave function in time. So basically, this function down here is what we did in class the other day, going from the time independent to time dependent.
From time to no time.
Yes, time to no time. So then it goes from time to independent. And yeah, I don't know.
Okay, let's thank Joe. Summarized content of like 3 lectures that I'm going to give in the future. Any questions?
On your third slide with content on it, so it says fifth postulate count continued.
Yep.
You said if you measure A, you're going to get the outcome AN, and then you immediately remeasure it, it will give the same value. Is that what that is saying?
Yep.
Okay.
Yep.
Yes. What was the name of cat owned by Schrödinger?
Oof. I do not remember.
Okay. What is or who is Schrödinger cat?
It's if you have a cat in a box with an isotope, a radioactive isotope, and you either know if the cat's alive or dead. It could be alive or dead because if the isotope decayed or not, killing the cat. But in other words, to know if the cat is dead, you have to open it. So you can't like know the position and that something like that.
You can't like know what state it's in.
Yeah.
Until
you open it. But when you open it, then
you change.
Yep.
Yes. I was not including it into lectures, but you guys maybe for curiosity browse through this or
yeah.
So your question has been answered now by Joey in the following sense. If you open the box and found the cat is alive, you close eyes, open eyes, it will not become dead in this instant of time.
Okay.
So if you remeasure the rate immediately, it will stay in the same eigenstate.
Okay.
Excellent discussion, more questions? If no, let's thank Joey once again. And it's time for Benjamin Jeffrey and Isaiah Siegfried. So they will tell a story about time dependence.
This one has pictures on it, so ours is the best. Without a doubt. So, we're going to be talking about postulate 6, which is basically time-dependent Schrödinger's equation. Not basically, it is actually. Okay, so the time variation of the state function of a system is given by the partial derivative of psi with respect to t of 1 over I cross h psi. That's a lot of letters. So psi is the wave equation, and it is dependent on the position, whatever you want to define that as. Time. H is the Hamiltonian, which we'll talk about in the next slide, and H cross is the reduced Planck's constant. It's pretty boring. The Hamiltonian is the quantum operator, the total energy in the system, which is simply the sum of the kinetic and potential energy. The potential energy is simply just some function of position in time. And the kinetic energy is usually given as momentum squared over 2 times the mass, or negative h cross squared over 2m times the Laplace operator squared, which the Laplace operator is simply the gradient function of position. So the probably most common example of this is the single non-relativistic particle example, which we simply plug in that Hamiltonian and we kind of rearrange the function of it. And it describes a single non-relativistic particle moving through an electric field of a more massive particle. Now, this over here, we can actually look at the time dependence of this equation. In the top 2 examples, you can see that while the left side is moving, the right is not moving. These are examples of stationary states or standing waves. Meanwhile, this bottom one, this right side is moving. This is a non-stationary state. These top 2 you will get not only as solutions to the time-dependent Schrödinger's equation, but also to the time-independent Schrödinger's equation. Meanwhile, this bottom one is only found as a solution to the time-dependent Schrödinger's equation. So, great.
And then finally, we're going to talk about the linearity of Schrödinger's time-dependent equation. I would briefly define that as, in the most simple way I probably could, just like a linear polymer or a constant coefficient in the equation that is able to be taken the derivative of or the integrand of that. So quantum mechanics has a unique characteristic, which is its linearity, while classical mechanics is nonlinear. There are a few exceptions being linear, like a simple harmonic wave, I believe it is. But more generally, mostly quantum mechanics is linear. This arises from that Schrödinger's equation is a linear differential equation. I have a couple of notes over here. Give me 1 second. back to that. The linearity of quantum mechanics is serendipitous because it allows the concept of superposition states, which is that a quantum state can be a linear combination of two or more states, or two or more other states. So it can be a wave and a particle at the same time, just like the Schrodinger's cat thing. It's technically 50% of both at the same time until you open it and actually observe it, which would become a particle. Another good example that Morgan used earlier is he explained like the particle in the box or the electron in the box. It will give you more probability rather than a definite answer. So it could be kind of anywhere in the box, but it won't tell you exactly where in that box the electron will be. It'll give you more of a probability.
Okay, let's thank both speakers. And it's a chance to ask them questions. No? Can we go to the nice movie with, yeah, that's fine. So it's really cool stuff that they have presented. The top two show probability distribution time independent. So wave function of probability distribution. And here it is time dependent. So each three examples are solutions of time dependent Schrodinger equation, which depends on position. And yes. So one should put brackets and put x, t. Right? But the question is, what is the criterion for the following? Like you see that solution of time-dependent Schrodinger equation can be time-dependent, truly time-dependent, as in lower row, or time-independent. So once again, time-dependent Schrodinger equation can give time-independent solution for the probability classifier. So how to, based on everything you have heard today in class, in which situation, for which initial states the probability distribution extracted from time-dependent Schrodinger equation will have time-independent character.
Say that again.
When time-dependent equation gives time-independent solution.
That when time equals 0?
No. If we allow time to propagate forward. And you kind of gave this answer. I'm kind of asking you to repeat it or sharpen and focus and highlight.
Does it depend on the initial conditions that you're given?
Yes. So which initial conditions will make a solution of time-dependent equation time-independent?
Is it that it's also a solution to the time-independent Schrodinger equation?
I like your train of thought. Yes. And what are solutions of time-independent Schrodinger equation?
When it's a standing wave?
Yes, eigenstates. So basically the answer, if your initial condition coincides with one of the eigenstates, 0 or 1, then the wave function will change in time, but probability distribution will not. So eigenstate doesn't change in time. And here I disagree with this label. It should be, probably it was something like psi 0 plus psi 1. So if it is a superposition, remember you guys were talking about superposition introduced. If initial state at time 0 is a superposition of more than one eigenstates, then the probability distribution will show time dependence. So we will go through this thing many times in course. It's just a little heads up. Anything else you always wanted to ask to Ben and Isaiah.
Clearly experts. Answer A.
Questions 1, questions 2, questions 3. Let's thank them once again. So, let me keep putting remarks. So, it was excellent work that I'm absolutely sure you will trust each other much more than myself. And you see that sometimes on the learning curve you do something better or worse, but you are improving, making feedback, and I think this summary of principles of quantum theory will help us to progress better in the following thing. Thank you for your effort. Everyone gets sufficient credit towards your final grade, and meeting it is dismissed.